The first example here, they ask you to use Jacobi method to find approximation solution. So let's check this example and how we're going to find approximate solution. So I'm going the first thing, I'm going to write down the functions here, which is 7x1, sorry, the system, 7x1 minus x2 equals 39. And the second one is going to be x1 minus 5x2 equal -9. So here is the system. Is going to be the same method. If you have 3 equations, 4, 5. So the first thing, I'm going to solve the first equations for x1. That's x1 is going to be 39 over 7 plus 1 over 7 x2. So this is the first one. If you want to convert this one to a decimal number, because we're going to work with decimal number, so that's mean. So this one, that's mean 39 divided by 7 is going to be, and they ask you to round your number and work with 4 significant digit accuracy. Round your answer to 3 decimal places. Let's work with the 3 decimal places. So this one is going to be x1 equal 5.571 plus 1 divided by 7 is going to be 0.1429. I'm rounding the number to 3 decimal places. So 42 must be 43. x2. So I'm just converting the fraction to a decimal number. So when I plug in x2, it's going to be easier to find. Now, the second one, I need to solve it from x2. So here's the second one. So it'll be x. Move the x2 to the other side. So it'll be 5x2 is going to be x1 plus 9. That's mean 5x2 is going to be x1 plus 9. Then divide by 5. So x2 is going to be 1 over 5 x1 plus 9 over 5. The same thing, I'm going to convert this one to a decimal. So 1 divided by 5 is 0.2. That's mean x2 is going to be 0.2 x1 plus 9 divided by 5. 9 divided by 5 is going to be 1.8. 1.8. So this is the second equation now to find the value of x2. Now we're going to create the table and we're going to check how we're going to approximate to the exact solution. So the table is going to be, here is the end. I'm going to start with x1. They're telling you here is start with take the 0 vector as initial approximation. That means x1 is 0 and x2 is 0. Let's do it on the next row. This is x1. Here is x2. With the first initial iteration, it's going to be 0, 0. Now let's start with the first one. The first iteration is going to be. How are we going to find that? I'm going to plug in. Be careful because we have 2 methods. For this method, you're gonna plug in. Here's x1, plug in. I need to find x1. That means I'm gonna plug in x2, which is 0. That means x1 is going to be 5.571. Now x2, I need to find x2. I'm gonna plug in x1, so it's going to be 1.8. This is the first iteration. Now the second one is going to be, I need to find x1, so I'm going to plug in x2. So here is the thing. So it's going to be 5.571 plus 0.4 times 0.143 times x2. I'm going to plug in x2 here, so 1.8. Close the parentheses. The result is going to be 5.8288. This is the second iteration. Now we're going to convert to the exact solution. Now I need to find x2, so I'm going to use this function. I'm going to plug in x1 here. Here is x1. That means it's going to be 0.2 times x1, which is 5.571, and plus 1.8. So it's going to be 29142. So here's 2.914. Just read the small places. Let's keep going to the third iteration. So until now, this one goes up. That means we reach number 6. This one goes up from 1.8 to 2.9. That means we convert to number 3. X2 is going to be goes to 3. X1 goes to 6. Let's check the third iteration. The third one, I'm going to plug in now. I need to find x1, and I'm going to plug in x2 here. I'm going to use the same one, this one, but I'm going to change 1.8 to x2, which is 2.9. So 2.914 is going to be 5.8987, which is around to 3 decimal. So 5.988. Let's plug in, find the x2. So we're going to plug in x1 here. X1 is going to be, here is this function, the second one. I'm just going to change the number here. I put in x1, which is 5.828. The result is going to be 2.965. So here is going to be 2.9656. So it's going to be 6. You see, I'm rounding this number, 2.9656 is going to be 2.966. See, this is going to 6, and this one going to 3. Let's do another iteration. That means when you need to find, first of all, find the x1, the function for x1, the function for x2. To find x1, you're going to use the value of x2. And to find x2, you're going to use the value of x1. So it's look like close. To find the new x1, you're going to use the x2. To find x2, you're going to use x1 and keep going. And your solution is going to be converged to the exact solution. So let's find another iteration, 5, and we see we're going to keep going to the 6, and this one going to the 3. Let's find another iteration. I'm going to find x1. I'm going to use x2 to find x1, the new x1. So I'm going to use this function, this one. Just going to change the number here to 966. So it's going to be 5995. 5.995. See, keep going up. Now let's find the value of x2. I'm going to use this function and change x1 to 5.988. 5.988. So it's going to be 2.99. 2.988. 2.997. So 998. You're gonna keep going. So if you keep going, you're not gonna pass the number 6 here and number 3 here. That means our solution from the top is conversion to number 6 for the x1, and x2 is conversion to number 3. That means the solution here is going to be 6 for x1 and the 3 for x2. 6 for x1 and 3 for x2. Let's check that. We have to write down, I think, comma 1, 2, 3. Comma 1, 2, 3. Oh, not this one. I'm plugging in the wrong one here. The first question. So 6, comma 0, 0, 0, not comma. 6.3 decimal, and this one 3.000. That's it for this one. Even if you do another iteration, it's going to be keep going to number 6. That's why it's called. This is going to help you when you're doing coding, when you're trying to make, like, you're not going to get, you don't want to get the exact solution, but you want to get approximate to exact solution. So this one is going to be easier when you're doing a code using my MATLAB. When you're going to learn the coding, this one is going to be easier when you create the exact method, because you're just going to use x1 and x2, and you're just going to do one loop to plug in x1 and x2 to converge to the exact solution. So when you get the result, you already know this one's going to be goes to convert to number 6, and this one converge to number 3. Even if you do the 5, it's going to keep going. A number here, which is less than 6, a number here less than 3. So this is Jacobi method. And you will see the solution keep going to the exact solution, which is 6 and 3. But if you check the other method, Gauss-Seidel method, it's going to be different. like we're going to learn that x1 and x2. Here is going to be the exact solution. The first value is going to be on this side. Like here's first x1. Then the second one is going to be here on the other side. So we're going to converge from both sides. x2, the same thing. The first x2 is going to be here. The second x2 is going to be here. So we're going to converge from this one, then it's going to be negative. x2, the same thing. Positive is going to be negative. Then it's going to be positive, it's going to be negative. Positive, negative. Keep going until we reach to the exact solution. The same thing here. That's the difference between Jacobi method and Gauss serial method. So how are we going to use Gauss serial method to find the solution? So here's the thing. We're going to do exactly the same thing. Convert the first equations and solve the first one for x1 and the second one for x2. These concepts. So let's work on the second method, which is Gauss serial method. Let's solve the second example. They ask you apply Gauss serial method to the given system. And the same thing, they ask you to take the zero vector as an initial approximation. And how many? We're going to round your answer to 3 decimal places. So here's the first one. 4.5 x1 minus 2.5 x2 equal 1. And the second one is x1 minus 3.5 x2 equal negative 1. So now we're going to use Gauss serial method. I'm going to solve the first one for x1. So I'm going to move x2 to the other side and divide by 4.5. So x1 is going to be 1 over 4.5 plus 2.5 over 4.5 x2. This is the first one. Let's simplify this one. 1 divided by 4.5 is going to be, here is x1 equal 0.22 plus, this one is going to be 0.1, 2.5 divided by 4.5 is going to be 0.5. So 0.556 x2. So this is the first equation I'm going to use. The second one is going to be, I'm going to solve this one for x2. Be careful, always the first equations for x1 and the second one for x2. The second one, we're going to solve it for x2. That means it's going to be here. x2 equal negative 1 over negative 3.5 x2 minus 1 over negative 3.5 x1. So for x2, so we're gonna move this one to the other side. So negative 1 over negative 3.5, and move this one is negative 1 over negative 3.5 x1. That means this one is going to be positive. So this one is going to be positive. 1 divided by 3.5. It's going to be 0 point. So x2, let's write down here. Second equation is going to be x2 equal 0.286 plus the same thing, 0 point, because 1 divided by 3.5, so also it's going to be 0.286 x1. That's it for this one. I have two equations. Now I'm going to create the table. But you can see where the difference is going to be. This is n, x1, x2. First iteration, we're going to start with the 0 vector. So 0, 0. Here is number 1. So here is the difference between this method, how it's going to work. I'm going to find x1, plug in x2 is 0. That means this is canceled. So the first one is going to be 0.222. So here is the thing, that's the difference. I have the new value for x1. To find the new value for x2, I'm not going to use this x1. I'm going to use the new x1. So the difference here, I'm not going to use, this is to find the x1. To find x2, I'm going to use this value. So it's going to work like this. So I'm going to plug in this value in this equations here. That means it's going to be 0.286 plus 0.286 times x1 is going to be 0.222. So the new value is going to be for the x2 0.3499. Check here 94. So it's going to be 10. That means this one is going to be 50. 49, which is going to be 50. 50. So here's the first one. So that's the difference between Gauss-Seidel and Jacobi method. We're going to do the same thing. The second iteration is going to be, now I need to find x1. So I'm going to use, here's x2. I'm going to plug in hit this x2 here. So it's going to be 0.222 plus 0.556 times x2, which is 0.350. So it's going to be 0.4166. So x1 is going to be 0.417. Rounding the number. Here is the new x1. We're going to find x2. So I'm going to plug in this value in x2. This is the equation. I'm going to change this number to 0.417. It's going to be 0.452, 0.4052. Just 5. Let's keep going. We're going to stop on this method until you're going to see the same number is going to be repeated. Let's keep going. We're going to find x1. The iteration is going to be use x2 to find x1. So let's plug in this one here. That's the equation. We're going to change this number to 0.405. 405. And it's going to be 0.447. This one is going to be 0.477, 4471. So 447. Now I'm going to use this x1 to get the x2. So here is the new, this one. I'm going to change this number to find the x2. Here's x1, so 0.447. So to be 0.413. Just to get on this number. 0.413 is going to be 14. So rounding the number. 0.4138, so it's going to be 414. Let's keep going. The fourth iteration. Let's plug in x2 here to find x1. That's mean I'm going to use this one and change this number to 414. 414. Going to be 0.452. So 0.452. Now we're going to use x1, the new x1, to find x2. Let's keep going. We're going to use this one to find x2 and change this number to 452. 452. 0415, which is the same thing almost. So it's going to be 0.4152. 415. Keep going to the fifth one. Let's find x1. We're going to use x2. That's mean use this function. Change the number to 415. 415. So it's going to be exactly the same number. 0.452. And you see there's 7, so let's do the 3. Round to 3 decimals, so it's going to be 3. Supposed to be round this one also here. 5, 5 here. Yes, I did round it here. So this is also 3. Now we're going to use x1 to find x2. Let's check this one. Let's mean this function. I'm going to change this one to 3. 0.4155. So it's going to be 0.415. 5, 6. Still, there's a little change here and change here. I think this is going to be the final solution. Let's do another iteration to make sure this is the right one. I'm gonna plug in x2 to find x1. So here is just gonna change this one to 6. So 3 decimal places. Do this one. This one is going to be here's 4, 5, 2, 7. X2, we got 4, 5. Yeah, this one is going to be 6. Oh, this one. Because 3 decimal places, so this one. Okay. Now I'm going to change the 5 to 6. So it's going to be exactly the same thing here. And we're not going to round, even if you round the number, you see 0.4532. Even if you round the number, this one's still 3. So 453. I'm going to use this one to find x2. So here is the function. I'm going to change this one. It's exactly the same number. It was 453, 453. So this one is going to be 0.416. That's mean x1 convergent to 0.453 and x2 convergent to 0.416. So that's the difference between Gauss-Seidel and Jacobi method. So it's going to be 0.453, 453. And the next one is going to be 0.416. 416. 53, 416. That's it. So how are we gonna stop on this method when even if you round the number, you see there is no change between x1 and x2. Here is x2. And it's gonna keep going the same thing. That's mean this x1 100% going to converge to this number because the change is going to be small number like 0.00. The change is going to be 0.00. You see 1. That's mean the change is going to be only on the 4th digit. And keep going change here on this the 6th digit, 7th digit. That's mean this number is going to convert 100% to this one, and x2 is going to be to 0.416. So they ask you here, compute the first 4 iteration. That's how it's going to be using the 0 vector as initial approximation. That's mean here is the 0 vector, so 100% this is 0, and the second one is going to be also 0. And we're going to find x1, x2, x3, and keep going. So we're going to start with the first initial. Here is 0 and 0. Then let's write down the first equation. Is going to be x1 minus 5, x2 equal 6, and 6x1 plus 5x2 equal 1. It's easy to find the exact solution, but we need to use Gauss-Seidel method. So I'm going to solve this one for x1. That's mean move x to the other side. So x1 is going to be 6 plus 5x2. This is I'm going to use to find the next number. Now, solve the second one to x2. That means x2 is going to be 1 over 6, so 1 over 5 minus 6 over 5 x2, x1. Let's simplify this one. So x2 is going to be 0.2, 1 over 5 minus 6 divided by 5 is going to be 1.2 x1. This is the second one. Let's create the table. There's n, x1, x2, and let's start with the 0, 0, 0. First iteration, you're going to use this x2 to find x1. So I'm going to plug in 0 here, so x1 is going to be 6. I'm going to use the 6 to find x2. So I'm going to plug in 6 here. So it's going to be 0.2 minus 1.2 times 6. It's going to be negative 7. It doesn't mean that this is wrong. The first x1 is 0. I'm talking about x2. So this is for x2. The first number is 0. The second number is negative 7. And you will see, we're going to keep going to the converge from both sides to the exact solution for x2. The same thing for x1. The first one for x1 is 0. The second one is, sorry, negative 7 from the other side. Negative 7 here. And we're going to keep converging to the exact solution for x2. For x1, 0, and the second one is 6. That means we're going to convert from both sides to the exact x1. So we got the second x2 is negative 7. Then the second iteration is going to be, I'm going to use x2 to find x1. I'm going to plug in negative 7 here. So it's going to be 6 plus 5 times negative 7. And the result is negative 29. So here is negative 29. So this one is not convergent, it's this convergent. That they mentioned that here. Diverge. That's means we're going to go to the opposite side. So negative 29. Negative 29, which is on x1 is going to be on this side. Negative 29. Let's use this one to find, to find x2. So I'm going to plug in with this one. Instead of 6, it's going to be negative 29. So it's going to be 35. How many iterations they ask you? 1, 2, 3, 4. 2 more. And the third one, you use 35 to find x1. No, I used the wrong equation, I think. The 35. Find x2. Here's to find x1. So to find x1, I'm going to plug in negative 7 here. Yeah, this is right. To find x2, plug in here negative 29, which is right. So 35. Now I'm gonna use x2, so I have to use this function. So it's going to be 35 here. It's going to be 108. This one, 108. 181. This is the third one. I'm going to use this value to find x2. That's mean to use this function. So this one is going to be 181 to be negative 217. Negative 217. Keep going. Fourth one, I'm going to use negative 217 to find x1. So here's this one. Going to change. It's a diverge. Negative 217. So give me negative 1079. Then use x1, the new x1 to find x2, which is this one. So it's going to be, change this number to negative 1079. Going to be 1,295. Let's check it out. I ask you just for iteration, that's mean this one is 6, this one is negative 7, second one is negative 29, and this one is 35, third one is 181. And here is negative 217. Fourth one is negative 1079. 295. There we go. So x1 is going to be negative 1079, comma, and x2 is 12. Did that really ask you the last thing? So okay, that's true. 1295. 295. When they ask you to show that the edge that it is, apply the horizontal to obtain a solution accurate. So you have to keep going. You're gonna keep going to find the approximate solution for this one. And they didn't give you how many iteration until you find that the difference between is going to be 0.001. So it's going to be long steps. Just keep going on this table until you find the same value. It's not going to change. Like x1, you're going to find another x1 exactly the same thing. This one, that you're going to stop. x2, you're going to find the same x2, and then you're going to stop. It's going to repeat it the same value. That's mean you have to stop until the value is going to be repeated.